organizers for putting on this lovely conference and for letting me speak. And thank you for everyone who's come at 9:30 in the morning. So today I want to talk about a project that I'm working on currently with Amy Jordan, that's quantizing the A-polynomial. And what I want to start off with is like just the definition of the thing that I'm trying to quantize, that we are quantizing. It's the A-polynomial. And I'll just say now for orientation, this A stands for affine, as far as I can tell. So this construction starts with the following definition. So X is going to be some topological space. G is going to be a reductive group. And I have the G character variety. Of X. And this I'll denote chi character of X. And this is just going to be, I'm going to look at homomorphisms, fundamental group of my space. Like this, I have this, and then I'm going to take the GIT quotient. So the GIT quotient. So I have, this is going to be like a major player in the story. This part right here, before I take the quotient, I'm going to just denote it R sub G of X. And this is called the representation variety. So what I'm going to do with this is I'm going to build a knot invariant. And what this is going to be is it's going to be a knot in the standard S3. And the construction is that I'm describing is for SL2C. And in particular, what I'm going to feed into this is I need to feed in some space. There's like an obvious space I can work with if I'm trying to build a knot invariant. And this is just the knot complement, which I'll call M sub K. And this will be S3 minus some tubular neighborhood of my embedded knot. So here is the idea behind this construction. The idea is that I have a torus sitting in as the boundary of this knot, or I guess this is just a torus in MK. And what I'm going to do is I'm going to use this, and I'm going to use the fact that inside every reductive group, including SLC, I have some maximal torus, so some Cartan. And together, these are going to let me simplify sort of the character variety of the knot complement itself. Is kind of hard to get our hands on. It can be really high dimensional. It can be very singular. So what I'm going to use is these two tools to simplify it some. I'll say also, I keep saying we, but this is done by people in the 90s. This is not my work. And so what I'll do is I'll start off with the space of representations from pi1 of this knot complement into G. What I'm going to do to simplify things a little bit for myself is I'm going to say, well, switch blue for the comedy. Is this, I've changed blues. How readable is the blue? Is it readable for words? Okay, cool. So pi1 of this thing is just Z squared, and I'm going to call that generators L and M. So here I'm going to require that this L and this M land inside a Borel. So I'm going to have this space. Let's call this space V. And from here, I have what I'll call chi of an eigenvalue map. And what I'm going to think of this landing in, so here, let's say what this map does. Here I have sort of the image of L and M, lambda inverse. And what this map is going to do is it's going to just send me to the this top eigenvalue. And where I'm going to think of this landing is in the Cartan character variety of my torus. So now I have two t's, they're different. And make sure I get it right. So I've done this, right? I have this space. I've shoved it into something significantly simpler. This here is just, it looks like t cross t, right? And so what I'm going to do is I'm going to look at an associated module. So it's going to be the module, which is the algebra of functions on this. And it's going to be acting on space. All right, I'll pause for a question because this is going kind of fast and maybe there's not time to formulate a question. Yeah.
This assumption that they land in the Borel, that's mild because like they commute, so can you always conjugate it that way?
Yeah, this is sort of, yeah. This is sort of a, yeah.
You're fixing a particular Borel, right?
Yeah, I'm fixing the upper triangular Borel. Yeah. Okay, that's a good question. So, okay. So it does have. Yeah, I think there. No, it's gonna have kernel. I mean, this V is gonna be like a plane curve in 2D space, and this is gonna be really high dimensional. So this is destructive. Okay, but I have this, these are good questions. I have this module which I've constructed. And this module, so first this thing, I'm in the case SL2C, so the Cartan is just C star. So this thing is just Laurent polynomials in these two variables. And this turns out to be something of the form just my original algebra mod and ideal. And here's the definition. So after normalization, this thing here is the A polynomial. Okay.
Was psi a closed map?
I don't remember. I'll say I will say I went through this, but this was like a lot of very non-trivial algebraic geometry goes into showing that this is like a not invariant actually, and that I'm not explaining.
So you take the closure of psi, that's why it's, as you said, that's why it's called the affine.
Oh yeah. Yeah, there's some.
What you wrote is correct. O of psi is the.
Quick question. This GIT quotient, are you taking stable points or anything? I'm worrying about stacky issues here.
There's a stacky version of the construction. You do have like bad points that have stabilizers. Like
They're finite, I assume. They're
Yeah.
and
this one, it's like it's just the higher Jordan blocks are them. So it turns out to be like 1, 1, and then plus or minus 1 in the corner.
that's not going to play any part. That's not going to obstruct anything because you're working.
No, it is something that you sometimes want to think about, but we won't have to. Yeah, we will secretly be working with the stack in the second half of the talk.
My recollection was that you had to like throw out the abelian part before you got the A polynomial, or you're,
This is actually, I've seen people do both.
yeah, but you're keeping.
Yeah, we can say. It won't come up in the construction. So he's asking, you always get a factor of L minus 1. And some people keep that factor of L minus 1 and some people throw it away. Even if you look at like the first 2 papers written about the A polynomial, they don't agree about what to keep. Okay, but my title is about quantizing this thing. So I'll say, why would I want to quantize this? So one sort of maybe the less interesting reason is that our quantization scheme, I guess approach actually leads to an algorithm for computing A. So maybe you can kind of get the flavor from this. This is extremely labor intensive to actually compute like an A polynomial, to sit down and do it, right? But the scheme I'm going to tell you about today, it's actually led us to make like a computer program where you can just input like a knot and get out something like this. So right now this is very labor intensive, and this quantization actually helps us. And then maybe a more exciting reason is that there's a conjecture called the AJ conjecture, which is due to Gauss and Gukov separately. Gukov's version is like the physicsy version, and Garofalidis is the mathy version. And what this is that if I look at another invariant called the color-Jones polynomial, which is beloved, and I look at its annihilation ideal. So this thing is telling me about this is the annihilation ideal, that this thing is actually generated by a quantization. But getting this quantization is really non-trivial. Tudor has a really nice approach using hyperbolic geometry that runs into some problems which he knew about and explains very well in his paper about it. But sort of having a quantization, having a nice algorithm for actually quantizing this is, you could imagine, like an important step to understanding this conjecture. So that's maybe a better like grant application reason for quantizing it. So now I want to talk about this scheme that we have for doing this quantization, and the sort of the setup is I'll say defect scheme TQP. Actually, when I was writing this talk, I realized a lot of people think of skeins as defects, and these defects are not just the skeins. Again, this is not just the same word twice. So what's going on with all these words, what I'm about to explain, is that my defect is how I'm going to introduce this parabolic reduction. So the fact that if I have G and T, I have some way of going in between them. So this shows up here. This eigenvalue map is sort of how I'm going to do this. So it's showing me my parabolic induction. The reason why I'm talking about skeins is that these are known to quantize the character variety of surfaces, and also three manifolds, and also the representation varieties. G, sigma. So these are known to do that. It's also, we know that they're factorization homology. If you know what factorization homology is, you know this is an important feature of skeins. If not, this gives us a lot of nice excision properties with our constructions. This is what sort of connects it to like stacky versions of the character variety. And then TQFT, the thing we really like about these is it lets us glue cobordisms. And then sort of as a special treat, we also get some connection to Crane-Yetter theory on surfaces. Okay, so that's why we're doing all of that.
Question?
Yeah.
Can you say a few words about what you mean by quantization in this setting?
Yeah. So
You asked that question as well.
yeah.
I mean, deformation quantization?
But like a physicist, what do you mean by quantization?
Yeah, it's like deformation quantization. So I guess this is, sorry, yeah, I'm gonna have to say it in math terms, but these are like commutative algebras. And I'm gonna be able to cook out some algebras, and when this is a manifold, some modules. And when I do the scanning construction, I'll get like a non-commutative version of this. And I'll have some parameter q, and I can send it to +or-1. I'll get back the commutative thing. So yeah, deformation quantization. These have a symplectic structure. Are there other questions?
This is a 3D DQFT.
So this is a categorified 3D TQFT. It's gonna, yeah, it would be like it's part of a 4D TQFT, which we haven't proven. Okay, so let me talk, I want to start talking about this skein stuff. So I'll give myself a little more space. So I want to talk about skein relations. So to me, when we're talking about skein relations, really what's going on is I have some category. I'm going to call this rib. This is going to be a category sort of ribbon graphs. This is my graphical calculus. And I'm going to color it by some other category. I'll have this. So I have some, I'll call this F sub A, some evaluation functor. And what is this gonna look like for us? This is called the Rashatigan-Faraya functor. Is it's gonna send on this side, my objects are gonna be sets of sort of configurations of colored points on some disk. So maybe V1, the N. So this is like an object in this category. This is another object in this category. My morphisms, I think the two morphisms in orange, just to keep things nice and I don't know, technicolor. So my morphisms are going to be some tangle in here. So I can have coupons, you know, I can go around however I like. So this is just to say I could have something really complicated in here. And one fact, how we want to construct this is we allow ourselves to have sums of these. So maybe some AI is 0 to k, and that could have different things here. So this is a morphism in this category. Put this here. But I won't have to edit my talk notes. And what this morphism will give us, or this functor will give us, is some morphism. Again, like this. And what we're going to say is that two of these things are going to be scan equivalent if and only if they're sent to the same thing by this functor. So this is this thing right here is my scan relation. So I'll say whenever I introduce these, there's two things I want to talk about. I want to tell you about them is first off, maybe you've seen when people have given talks to you before about skein relations, you've maybe just seen them write something like this. And they're like, this is a skein relation is this. This fits into this framework. It's when A is rep QSL2 after a little bit of work. So this is like a sort of an example of a skein relation, but there's also a lot of skein relations in here that are just, I would say, bookkeeping. So an example of another one is, say, I just have the coupons F and G like this. This should be equivalent to just the same thing with colored like this. So these two are not isotopic, but we want to think of them as the same morphism, right? Okay. So these are my skein relations. What I want to explain now is how do I add defects to this story? And Sorry, I'm so short, a lot of stuff is gonna be hidden when I'm writing. Okay, so. What do defects do? In the original case, my algebraic input here is a ribbon category. Now, my input is gonna be, so my defects, what I want them to do is I want them to bring me between two different ribbon categories. So it's gonna be some morphism. And in particular, this is gonna be a one morphism in BR10s. So the data of this is in a second, and maybe you're more familiar with this as L2 of cat. BR. And what such a thing is it's just a functor between this tensor product to M a category, but not just the category, but its Drinfeld center. Yeah, I usually do, I just demand it's pivotal. I want to be able to do like surface skein stuff with it. And this functor it's the data of H, some functor just between the underlying categories, and then J, which I won't use, but I'll just say what it is a half braiding. So I have this. And how am I gonna go about it? Is I need to build something that goes from some version of this ribbon category to M. And what I'm gonna do, how much space do I have? Is I'm gonna take the picture that I drew before over there. And so I'm gonna take this picture, right? This is what sort of the morphisms in my graphical calculus look like. And I'm gonna put an interface in here. So I'm gonna work with like a stratified version of this disk, and I'll say this side is A world, this side is C world, and in the middle I have M. And now I can again have my morphisms. On this side, I need to have objects in my A category. This side, they need to be in C. Like this. And I can have, coupons connecting. In particular, I can go through my defect like this. Right? Is it clear? I can have stuff on both sides and I can have stuff passing through. So this is my new picture, and I allow myself to have sums of these things, finite sums. And what I'm gonna do is before I want to send this to some just morphism in my target category or in my sort of coefficient category. And what it's going to do now is I'm going to just send it from the tensor product A, C, H, A. Some morphism like that. And just as before, I'm going to say that two of these, so my skein relation is just again from the kernel of this thing.
The Drinfeld center.
Yeah. Wait. Oh, this one?
Yes, you have H.
So this is, I have two functors going on. One of them is to the Drinfeld center and the other is not. So H, yeah, I guess what I'm doing, yeah. So I'm, yeah. That's a good question, is where is the functor too? Are there other questions? Yeah.
Only interested in skeins that come from A and C, or are you also interested in skeins that may have something on the boundary?
In so David and I have, I would say, argued about this. In the construction, you can set it up so there's either. It just depends on what defect, like what category you take an M, you can have it automatically be either. We don't need stuff to be living in the defect. We can just have it be like the image of stuff in the bowl. But you could set it up so that you could have stuff in the defect.
The point where it crosses, you decorate with a morphism from M.
Yeah. So this thing here, there should be something. And it should be a morphism in M, right? And I just, all of the edges that are coming from outside, I just use H. So like if this one was V, W, and U, and say they're all like ingoing like this, then G is gonna be from H. V to W. Oh, the other way, U, insert W. The unit.
Okay, that's different from what I thought. I thought you would apply M to one side and then have a morphism to C, but that's more general.
Yeah, we should talk more because I know we both have setups for how this goes. But yeah, this is how I do it. Okay, so now I've defined skein relations. There's a like a cascade of definitions that happens that I can do now. One time when I was giving a talk, they actually had to pile up like tables for me to stand on. Okay, so let's have in a 3 manifold. Oh yeah, I want to give myself a name here. This thing, like this here, I'm going to call an M labeling or coloring of this, right? So all my points, they're colored. So X, an M labeling of the boundary of N. What I'm going to have is my relative. I should write this is with surface defects. So my relative skein module is going to be SK M over X. And this is going to be the space of all, let's say this is the boundary of N. And, you know, N is something exciting up here. And I have X to a bunch of points. It's going to be all of the span of all my skeins in here. And then it's going to be up to skein relations. On any time I can embed a disk into here. So this is my relative skein module. Yeah. So that was the cough. So this is my relative skein module. From this, so here's my first definition. My second one is going to be, so for sigma, a surface, I'm going to have my skein category. So now this is a surface. The surface now have line defects.
Your first one has a defect in it? somewhere?
Yeah, I didn't draw it. Yeah. Yeah. So now I can have a surface on the boundary. That's part of the data of N. So N has a defect in it. So N is like a stratified labeled manifold, 3 manifold, the surface defect. And you didn't ask, but maybe you might have asked, it can sort of my defects can touch the boundary. Okay, so this is a surface now with these defects also. So my skein category is going to have, so my objects are just going to be, M labelings. And my homomorphisms in this category from X to Y, these are both going to be labelings, is going to be this relative skein module in the surface. It's this joint union Y. So here I've put one on the bottom half of this thickening and the other one on the top half. So now I have a skein category. Let me put a little defect around this so you know it's important. Okay, and now I've talked about the first two words in this section. I want to now talk about the third, TQ of T. So this, I said, gives me a categorified 2 + 1 TQ of T. You may want to know what happens on cobordisms. So pull down this board. So on cobordisms, here, we'll just define it. So if I have sigma 0 and sigma 1, the cobordism. Just, I think we all think about cobordisms in this room. Just to set the convention, this means that the boundary has a decomposition like this, and one of them, I think of reversing the orientation.
Sorry.
Yeah.
You don't still think of N as stratified, or do you?
I do. So maybe I could write this really big somewhere, as N is always going to be stratified. And the non-stratified version of this is worked out already by someone, by Jordan, David, and Pavel, actually. And-
Say,
and other-
Walker and Theo Johnson Fried, yeah.
Yeah, I was thinking, yeah. Yeah, part of it that I use later, it's worked out otherwise. Yeah, so this is all always stratified. So this is a cobordism with defects. What I have here now is I'm going to make a functor like this, and it's going to be from stratified skein category from 0 up. What? So this thing, and it's going to send, here I have some X, here I have some Y. And it's gonna, the reason I just wrote it as this with an underline is it's really the functor version of this relative skein module. So it's gonna be relative skein module. Okay, I'll say we can also write equivalently, I could have written it like this from in category of sigma 1, 0. I could also write it as a just a normal functor from the skein category of the outgoing to the incoming, where this hat means that I'm looking at pre-sheets on this thing. Okay, I have this. And now the proposition is that this sigma going to skein cat, sigma in going to this relative skein module is yeah. What did I write? What did I write? What did I write? Where did I write it? Yeah, this is a categorified. This one, Q of T. So by this, I mean, this is going to be a functor from Bourdisms, maybe Q3 to something here, which is it's called bimod. It's just that's these pre-sheaf value functors. Thanks. Okay. Now I want to talk about what is being quantized here. I've given you a bunch of definitions. I'm going to hide some of those definitions. So I've set up this big framework, and my goal was to quantize something. Let me start talking about what's been quantized and by what. So what was so I had these character varieties, right? One of the character varieties that I cared about, and I wrote a little bit here, a subset, is the G character variety of M sub K. And now I'm quantizing, so this is something I'm doing on the algebra of functions on this. So this is quantized by this relative skein module, rep QG. So here, in this story, when I'm not thinking about this Borel yet, I don't have any defects, right? Everything's G. So now I don't need to write a defect here, I just need to write a ribbon category. So this is the relative skein module. Sort of an empty boundary condition. The other thing I was caring about a lot was this algebra, the algebra of functions on this thing. And this is being quantized. Well, I can write the same thing here. Now it's rep QT. I can torus with an empty boundary component. And now this, right, this is times 0, 1. This thing here, I think we see a lot in our field that if I have some construction on an n manifold and I put in like an n-1 manifold times an interval, I get some extra structure. This is kind of a general thing that happens a lot. Here, the same thing happens because my 3 manifold is just a cylinder. I get what's called a skein algebra. So I'll just shorten this to T. This. So this is this definition. And this one also gets called the skein module. Okay, so these are our 2 main players and how they get quantized. And I'll say this is not like just totally for free that this is the quantization. There's a lot of work done to prove this. And some of the people who I should mention is Pertezzi, Marche, Bullock has also nice stuff on it. Bullock, Cora, and I'm sure more names than I could write down, just to show that this sort of quantization procedure works and is true. So I have these 2 things. It turns out actually the main juicy thing that we want to quantize is this eigenvalue map, right? Which is what put us between this like G story and this T story. So this eigenvalue map is going to be quantized by my defect, which goes between rep QG, rep QT, via some category rep QC for this thing. Here is how this quantization goes. And this whole system, I'm gonna call sort of a fancier B. Other questions on this?
Is there a way, intuitive way of thinking about this, using Borel as your kind of interface as specifying that these loops live in the Borel?
Sort of in the relative.
Yeah, like you
Yeah.
kind of restrict to a certain class of people there and.
Yeah, yeah, this is actually something I thought, so maybe is your question like, should I think about this Borel as
Yeah, that Borel is like
is
that
this
Borel.
part? Yeah, so
Yeah.
it is this Borel. You're asking, is it this part or is it this part?
Yeah, is that bottom description on the.
No, I really think it's more so the eigenvalue map. Yeah, because it's, I mean, the way to think, my intuition behind this is, it's really, maybe let me draw a picture. Let me erase that and draw a picture. It's really what's letting us have like something with T acting on something with G, right?
One side is this is us. Here.
Oh wait, or do you mean, can I do it in the other direction?
No, I think I'm asking the question that you're answering.
Yeah, so here's the picture I would have for what this defect is doing for us. Is we have I'm gonna try to draw a trefoil. Okay, so we have our not complement, right? So this is like S3 minus my not, right? And this is all in the G world. But what I want to do is I want to act on this by sort of just a thickened torus, right? And somehow this is all in the T land. I've changed my colors around. This is in the T land, and the way that I'm going to do that is I'm going to put a sort of, imagine this is like a parallel copy of my knot, like this with a B defect, so that here actually I can do this interface, this action.
So the big effect is like on the.
Yeah. So maybe this is the perfect. We're all on the same page, because this is the segue into what I want to talk about. Yeah.
Sorry. I think I could have tried to do with something like this to think of it as W instead of T.
Yeah.
I think that like T mod W looks a lot like G mod G.
Yeah.
Why, like, seems like slightly, maybe this is better, but I don't quite know why this is better.
Yeah. So I know. So the reason that they do it in the original, like in the original construction of the A-polynomial, they do pass the T cross T instead of T cross T mod W. Right? If this was G right here, I guess the question is, if this was G, like this whole thing would be mod W. So maybe I'll do this in another color, so I could get mod W here if this was G. And I think your question is, what, couldn't I have just done the construction like that? When, I mean, you'll have to go ask them why they didn't. It's just nicer to not have this quotient. This is the Val group. Another reason that I want to do it in this world is that if this is just T, another way to think about this construction is that because my GIT quotient, my action is conjugation, T is commutative, this is just R T pi, right? And this is quantized by the internal skein algebra. So I'll talk to Theo for a second. This is by the internal skein algebra, which has better gluing properties than just the skein algebra. So this is like a really practical reason not to have this quotient. There are other questions? We're doing fine on time. So we won't miss coffee if you ask a question.
Can you give an explicit meaning of what it means to say that gain module is quantization of the left side? Like, is it like Hochschild homology, or like, what exactly do you do to the right to get the left?
I think like this as I can write this down explicitly with like generators and relations, and I set q to -1. And I get this. So it's like, it's a very.
The right-hand
unfancy-
side is a vector space in particular. It's a module.
Yeah, so I will get the same, so I won't get the algebra structure on this. But I will get this things, like the module structure of, like. This, once I add my defect here, right, I have an action of this on this. And when I take the classical limit, which is really just like plug in. I recover the module of like this, acting on not exactly this thing, but on sort of this thing.
I guess another way to get a question is that, you know, for the quantum group, you have this integral version, which is defined over Z, like BD inverse. And then I would imagine that I'd have my skein modules, which are modules over ZBB inverse. And so I could actually specify B to be a value Q, which is in C, Q could be 1, Q could be whatever. So then in that way, I would literally have some deformation of something of that. Is that?
Yeah, that's the right way to be thinking about it.
Say the geometry again, what's the shape of B?
So of B is also a torus.
B is also a torus.
Yeah, so B is like the torus. That's like a tubular neighborhood of this.
Right. Sorry, it's the boundary of the tubular neighborhood of T, is that what it is?
Yeah. So this is, yeah. So this is like, I don't know what you like to do for. So this is like the boundary. The neighborhood of the embedding of the map. Okay. So I want to talk some about, so one thing I want to make it clear is this procedure, it may not seem like it, but like this is, we have enough tools that this is explicit enough that you can explain to a computer how to do it. Right? This is a really explicit computation. And in fact, it's like an algorithm that like exists, it is code that exists and is on my laptop. So the goal of the algorithm is, so I have this skein algebra coefficients in T of the torus acting on the skein module of this MK. Maybe I'll give another name to something. Like this. I thickened my thickened torus, so maybe I'll write it really big. Gain module of my MK glued along this boundary component with this TB. So let's call this thing TB. So my goal is I have this, and what I in particular want to look at is the submodule generated by the empty skein in here. Right, so I want what happens when I find my orange chalk and I have sort of my action is I can have some skein in here and I include it and it becomes some skein in the boundary here, but I'm just acting on, I have nothing else here. So this is really what I'm going to be doing. So I think I will not go into as many details as I could. So I'll just say, what is the procedure? So the first step is to take an ideal triangulation of this MK with the Bohr's, the defect, the T halo. Right? So my ideal triangulation like this. And what I want to do is, so an ideal triangulation, what this part means is that my vertices form the boundary. So what I'm going to do is I'm going to truncate these vertices. I'm sorry if you're taking notes somewhere you can't erase. And I'm going to put a B defect around each one of them. So now what I have is sort of these boundary components like this. And here I'll have T, 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 and in here it's G. Right? So what I'll do is I have this, right? Thanks to the work of JLSS, Jordan, Lee, Schrader, and Shapiro, these edges. So when I say these edges, I really mean all these edges that I've drawn in white. These generate a localization of the Skane algebra with this B coefficients in this of a sort of, I'll just call this thing. This will be my little cartoon for this thing. Okay, and what's really important here is that actually this is going to be a quantum torus, which means everything Q commutes, and I'll call this just T sub this thing. Okay, so I'll do an ideal triangulation like this, and let's say I have all of these triangulations, tetrahedrons here, right? They're setting off, they're all, you know, with punctures and with their B defects, you know, this. And what I'm going to do after this is I'll glue. Here I'm using the fact that I have a PQFT and factorization homology. And what this gluing looks like is every face here, which is connected here, I'm doing some boundary connect sum. And I'm going to get a bunch of extra generators. So sort of, I'll have a bunch of new generators that go between here, 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 right? They're, what all these generators are doing is saying like this face here is connected to here. So there are skeins that can go between them. And now what I have is a big quantum torus. So maybe I'll just call this T of my knot, okay? And this is going to have, just to be really concrete, this is going to be 24 times the number of tetrahedrons generators. And then the third step before we go to coffee is going to be, or I guess maybe the third step is take T invariance. And what this means is that here, maybe you noticed I did a sort of a switcheroo. I now am letting my skeins have endpoints, right? Like this line is not a loop, it's just a line. And so what this means is like I only allow loops. So if I had two skeins that were coming in at a boundary, sort of instead I get something that misses that boundary component like that. And then the fourth step, which I'm very happy to talk about because I've obsessed over for like a year and a half, is to take, so quotient by, first I need, I'll just say, because it's the 5-minute mark, I'm gonna just say many things. Sorts of things I want to quotient by is a thing saying if I glued this face to this face, then this edge becomes this edge. That's one thing I want to do. Another thing I want to do is I want to close up these little holes that I opened. That's another thing I want to do. Another thing I want to do is I want to fill in each tetrahedron. That's another part of the quotient. Another thing I want to do is, you may have noticed when I do this gluing, I introduce some new handles. I want to close those. So those are, I have to take a lot of quotients. And what I end up with, T, K, mod, so I'm taking these invariants, I mod some huge ideal here. And what this ends up looking like, 1/2 M equals Q ML mod some ideal. Make you like that. And so this ideal is where the quantum A polynomial lives. And this step is this is the expensive step. This is the Grosvenor basis step. Okay, cool. I'm gonna stop there, even though he's not standing.